All right. I guess we are ready to start. Welcome after lunch. Welcome to Creative Corner. And now, with the first session, Mate will be talking about a CDB upgrade.
Hi everyone, my name is Mattias Ljunggren. I am a software engineer at NSO Engineering. I joined TRF in 2011 and ended up working for Cisco. I have been working in many parts of NSO, but for the last few years I have focused on CDB. How to make it faster and how to make it better. So I did a similar presentation half a year ago after the 6.2 release. And this is an extension of that presentation since we just released the 6.3 release. The agenda. So what have we done? I'm going to talk about the work we have done since 6.1, that is 6.2 and 6.3. I am going to do some kind of a deep dive. I'm going to talk about a novel key data structure that is called the upgrade tree. We are then going to look at two new options for the reload action and some logging improvements. And the exciting things, the results, of course. And we will end up with a number of conclusions. Oh, sorry. Improve the analysis, 6.2. So at the very start of this project, we divided it into two parts. The first part, the goal of the first part was to improve the analysis of schema changes, what has been changed and what we must do. And the second part, which is included in the 6.3 release, is to improve the execution. Upgrade tree. So the outcome of the improve the analysis part is a kind of a diff set for schemas. So it contains a complete description of what has to be done in order to make the old database fit into the new schema. And it's an evolution of the Merkle trees that we introduced in the migrate action in 5.5 release. The reload action has two new input parameters, schema report and dry run. And we now have a separate upgrade log. So all upgrade related log entries go into this upgrade log. We also log more information, so the upgrade process in itself becomes more transparent. So what about CPU core utilization? So this picture is a fairly good description of how CDB upgrade looked before the 6.3 release. So one core is doing most of the job while the others are idling. So the bad news in 6.1 and earlier is that CDB has a legacy code base in some aspect, and it's partly limited by single core design choices taken or made in the past. So once you start to utilize all the cores, you might come up against multi-core anti-patterns, such as singleton entities. You have a single serve, you have a single file, etc. You have excessive data sharing, excessive interaction between processes, and you might generate an excessive amount of objects, which might cause the garbage collector to overload. Well, that doesn't sound very good. The good news, however, is that NSO is written to a great extent in Erlang, which is the perfect fit for going multi-core. So that's the happy end of the story, which brings us to 6.3 release, improve the execution. Multi-core support. The major subtasks in CDB upgrade now utilize all available cores. There is no reason holding back while stuck in this dead zone of no transactions. Improved internal data structures. Internal data structures have been given a major overhaul. This is a natural and necessary evolution, since as the deployment size for NSO has grown a lot, the number of devices, the number of namespaces, etc. So the initial choice of data structures may not be valid anymore. In a sense, they are obsolete. The choice has become obsolete. And we also added a liveliness indicator in the progress trace for tasks with very long duration, once every minute, so you don't experience this total silence from NSO for a very, very long time. So let's talk a little bit about CDB upgrade, what it is and what it isn't. So in order to do that, I want to frame the concept by relating it to two similar but different operations. So the first one is when we want to add something to the schema. We have this action called packages add, which, although rather limited as for now, it adds one or more nel packages. It doesn't do any upgrade because it's not allowed to do. The second operation is when we do a device migration, which is kind of the opposite of the first one because it doesn't change the schema in any way. It just do a limited device migration from one schema to one device model to another. And the third operation is the actual CDB upgrade, which modifies the schema and also the configuration if necessary. So here is a beautiful picture of CDB upgrade. And as CDB upgrade, it comes in two flavors: when you start up the system or as an action. And so they are very similar. In this picture, we use the action. And as you can see in the upper right corner, this operation permits arbitrary modifications to the schema. You can modify namespaces, you can delete, you can add. And since any part of the schema might be changed, all transactions must be stopped first. And this is done by starting an internal upgrade protocol which orchestrates the upgrade, making sure to stop all transactions before loading the new schema. And when the new schema has been loaded, the old content or the contents of CDB must be made to fit the new schema. And this often requires work to be done by CDB. And we call that upgrade work. It's an abstract term. The work that must be done to convert the old base to comply with the new schema. So it's not the same thing as the schema changes, but it's related. So here we can see some examples of upgrade work. Change the data type, change the node type, number of keys, etc. And all but the last example are direct consequences of changes in the YANG file. The last one may be emitted by the conft process itself, because instance identifiers, they are more or less like a void pointer in C. They might refer to anything. So we have to check them. And here we can see a number of simple YANG changes. So the first example, it's a data type that is widened. And this is not correct, actually. So the first one does require upgrade work, but not because of it's not because the value doesn't fit. It's because the representation has to be changed. So this might very well be the situation in the future. The second example is the opposite of the first one, and the data type is narrowed, and then of course this requires upgrade work. We have to check every instance to see if it fits into the new type, even though we also have to change the data type. The third one, we change the node type from a container to list. Of course, it requires upgrade work. And then in the fourth example, we relax a validation constraint. And that doesn't need any work. Here is an outline of the upgrade process, a very simple sequence, high-level box, a sequence of boxes. And we have introduced a new box, the green box in the middle with the schema analysis. So now I am going to speak briefly about the situation before our work started in order to understand why we did it. So there was some kind of schema change analysis in 6.1, but it was not always available. It was incomplete. Lots of things were missing, and it was very difficult to understand. At least that was my opinion about it. And we didn't have any. There was no way to decide whether or not we should re-evaluate a specific validation constraint. So we basically always re-evaluated every validation constraint, which is of course is expensive. Also, we didn't have any means to detect whether or not we had a new validation constraint in a new added subtree of young nodes. So it would be nice to have some kind of a oracle to ask when you're about to iterate through the whole database. What must we change and what should be deleted? It would be nice to just having the means to ask, should we go down this path or are we done? So it should be nice to it should also be nice to have some kind of a diff set so we know the different changes made to the schema, just like we have in a standard diff set where we have added nodes, we have deleted nodes, changed nodes, etc. So, upgrade tree. It's a tree of upgrade work items. Very simple. It is similar in structure to the old schema, but it's not only the old schema. It's a subgraph of the old schema and some parts of the new schema. And the schema path is used as a key for lookups. So one of the most important use cases for it is, of course, to prune when we descend down the tree, if we should descend or not. So we used it as a pruning mechanism. So here is a very simple picture of how it might look. So on the left you will see an abstract schema with three subtrees, A, B, and C. And apparently we have done something to the schema. So we have some upgrade work in the C subtree. Something has to be done. And the corresponding upgrade tree will only have a subtree in the C part. So we know that. We don't have to go down to the A or the B for all instance data because there is nothing to do. Okay, here is on the left side you can find a very simple Young model, the old version and the new version. You can see that we have added some nodes in the beginning and we have changed some nodes and we have deleted some nodes. And on the right side you can find the corresponding external representation of an upgrade tree, which will be printed in the upgrade log, of course, so you can inspect it afterwards, so you can understand why it took so long time, or if it didn't take so long time, or it's something that you didn't understand. Here are a couple of notes about how upgrade trees are built. So information is propagated from the bottom to the top, just like a Merkle tree. It's based on some form of digest for a node, where any child nodes are included, of course, their digests. We have to process global dependencies in a special way. And we have global dependencies. I mean, with global dependencies, I mean non-local dependencies. We have references from one part of the schema to another part of the schema, and we have to handle that. But we have that information. It is provided by the compiler, and if the compiler is not able to provide us with that information, we make sure that the corresponding validation constraint is re-evaluated. But in most cases, we have that information, which is nice. So that was the deep dive. So now we move on to the packages reload action. Very concrete stuff. So we have a new input parameter. It was added in 6.2 release. It is called report, which will generate a report on the schema changes, and it's similar to the. It used the same structure as the migrate action, the modified path structure, which is nice. You can see what is done, what is changed. This is slightly different to the upgrade tree. This is what is changed, not what is done. We also added a dry run input parameter. So you can do a package upgrade, but nothing will be changed in terms of schema or configuration. So yeah, mind you, it's not hitless yet. It might become hitless in the future, but not yet. So all transactions will be stopped, etc. Logging improvements. As I stated earlier, we have now a separate upgrade log. We print upgrade trees and schema diff tree. And every upgrade is the last thing that is printed in the upgrade log for an upgrade is something called upgrade event counters. So internally, CDB maintains a set of counters, one for each type of upgrade work. And every time a configuration node has work performed on it, we increment this counter. And at the very end, we just print all the counters, which serves also like a summary or a digest of an upgrade. Here you can see the upgrade tree. It's something that you probably won't study every time, but it's good to have when something goes wrong or if you don't understand. And here's an example of the upgrade event counters. Not very interesting. But this one is. So the results here come from the system test of the core function pack team in San Jose. And the first one is the huge CDB. It's a big system, 700K services, and approximately, I think it's 28 gigabytes or 34 gigabytes, so it's quite big. And you can see a dramatic, I would say, reduction in time from 16 hours to 1.5 hours for 6.2 and half an hour for 6.3. We have a smaller one. It's about 4 or 5 gigabytes and a similar reduction. So this is an interesting diagram, I think. It depicts a critical section for package reload. That is the duration when no transactions are allowed. and how we spend the time during this duration. So we start with a blue bar, we load the new schema, and then for the 6.1 release, we actually do the upgrade, a long time going through the database, iterate and do lots of stuff. And then we apply the upgrade transaction at the very end. And as a note here, this is not, I mean, this is an imagined scale here, just to fit the screen and to describe what has happened. In the 6.2 release, we introduced the analysis phase. It's the new green bar, and as a consequence of that, the orange bar is much shorter. And the red bar is also shorter because we have less validations that we have to validate. And also because I think a lot of good work was done in the validation phase itself. In the 6.3 release, we went multi-core. So we had yet another reduction. So what's the next step? So in order to decide that, we might consider the law of diminishing returns, for example. Because should we keep investing in making the orange bar even smaller? Is it the best choice? Should we get the best return of investment by doing that? Or should we do something else? And I think this is an example of Amdahl's law, because the blue bar, the load of packages bar, it's a sequential process for now. So we might do something there. So we have different options here. We might reduce the blue bar by doing it more efficiently. Another alternative would be to try to move the blue and the green bar out of the critical region, if it's possible. And yes, so we don't know yet. We have to think about it. And that leads me to future. So we will continue to improve performance, of course. We will probably shift focus a bit to hitless operations. And yes, improved support for custom upgrade code. It tends to be a lot of code and not so easy to do it. And conclusions. Yeah, the first one is thorough analysis pays off big time. And this is probably even more important in a multi-core environment. It seems like bad decisions seems to be exacerbated when you have 100 cores doing something than you have one core. Quantity has a quality of its own. So when you get such a big reduction, it's more than a reduction in time. You will probably see a change in behavior, in operational behavior pattern. It's so difficult. I guess it's very difficult to schedule a 16 or 30-hour upgrade, but schedule a half an hour upgrade is a completely different thing. Staying in Erlang, it's all about algorithm and data structures. That is nice, I think. Yes. brings me back to my teammate Fu Lin. So it's me and Fu who have been working with this over the last year, more or less. So, any questions?